Welcome everyone to a new episode of The Solar Journey. My guest today is Martin Green, a scientist from Australia. Some or many or most or all people in the industry call him the most famous professor in photovoltaics of the world. And I certainly agree. Welcome, Martin.
Oh, thank you, Torsten.
Yeah, so before we get started, let me add some words. I personally also was strongly involved by the work of our guest today, like many others, I guess. I studied physics in Karlsruhe in Germany, and my professor back then, Peter Würfel, that's in 1993, so roughly 31 years ago, he mentioned that there's this book by this Australian professor, Martin Green, and it would be a good read in addition to his own lecture. So I thought, if Peter proposes a book from Australia, so far away from Germany, it must be a good one. And that made me actually write not only my very first emails, but also to spend 1.5 years in Australia to do my Diplomarbeit, master thesis in Australia. Martin, your former co-worker Andrew Blakos was faster, so he saved you from my presence. This is why I did not go to Sydney to see the Opera House, but Canberra, where I did spend a wonderful time and got a great training in solar cell physics, also by Andres Cravers. I'm sure you know him as well. But I surely think you have better beaches. Now, as I introduced you as famous, do you regard yourself as famous? And I guess the correct answer should be yes. And what's it like to be so famous?
Yeah, one of my colleagues used to say I was famous in my own lunchbox. I'm famous in the photovoltaic community, but not as well known outside of it. Although here in Sydney, we of course have our iconic Sydney Harbour, and it was just announced earlier this month that one of the new Sydney ferries that sails on this iconic harbour is going to be named the Martin Green. So right. And there's a bit of a story, you know, in the ferry just describing why it's called Martin Green. So I'm probably about to become more famous in Sydney than I have been in the past.
All right, that's a nice one. Very good. Yeah. So the Australian Centre for Advanced Photovoltaics recently launched the ACAP Industry Consortium, and yeah, JA Solar and ICO have signed on. What does this mean for solar research at the UNSW, your home university?
Yeah, so I started ACAP in 2013 and was director for 10 years, but I've just handed over to Professor Renata Egan, and Renata has organised funding to 2030. So, you know, that's unusual to be able to secure funding for such a long period for a centre like this. But one of the conditions is we have to have more industry money coming in as time goes on. So the money given to us by the government decreases, and we're supposed to build up our industry funds. So we have very good contacts within the manufacturing industry, particularly in China, since it's mostly located there. But that's because a number of my students actually founded that industry. And then in 2000, we started the world's first undergraduate engineering program in photovoltaic engineering. And over 1,000 Chinese nationals have taken that program and then go back to work in the photovoltaic industry in China. So Australian universities are very dependent upon overseas fee-paying students to make up their budget. And Chinese students have been quite interested in coming to Australia to study photovoltaics. So we've done quite well in that area.
Yeah. So what's the payoff for companies like JA and ICO and for all the others that will join the consortium?
Yeah, it's just you know, being in contact with our research centre, being kept up to date with the progress in the different areas that we're working on. Student recruitment is a big factor, so we're facilitating student recruitment, and in fact, part of their membership fee will pay the stipend of a PhD student. So we'll have, you know, it won't be like one company will own one PhD student, but we'll have this pool of PhD students, many of which are Chinese nationals as well with our PhD cohort. And, you know, they'll be able to do things like spend vacations at one or other of the consortium members as well. So it'll be a chance for recruiting some of the top people coming through our program.
And how do you go about the setting the topics in at ACAP? Is that a bilateral discussion, or how do you focus? Do you decide on the focus topics?
Yes, well, ACAP actually involves, gee, let's get the number right, I think it's 5 other Australian universities, as well as our Commonwealth Scientific and Industrial Research Organisation, which is a big government-funded research, or massive government-funded research organisation, who are interested in photovoltaics in 2 of their centres. So it involves a lot of people. So each of the universities has a node leader, and they propose topics that they're interested in having supported by ACAP, and then we have a big management committee meeting that decides the topics we want to put up to our steering committee, and the steering committee has the final say in what topics ACAP actually funds. So it's a fairly, you know, extensive process in selecting the topic areas. So, you know, University of New South Wales is where the ACAP is hosted, but other universities like Australian National University that you mentioned before, which is a very strong program in the Silicon and perovskite area, they're one of our members, as well as Monash down in Melbourne and the University of Melbourne itself, which are very strong in the perovskite area and organic semiconductor area, and then the University of Queensland, which is also strong in organic and perovskite semiconductors. So we have a program that spans the silicon and thin film areas.
You just mentioned a few times the role of Chinese students and the Chinese industry. So, and you've been a very formative figure in the establishment of the Chinese PV industry, and we'll come back on that role a little bit later. Here at the Solar Journey, we like to look into how people first got involved in PV. And you also were a person at some point where you didn't do PV. Hard to imagine. But what can you tell us about your early studies and what drew you to PV?
Yeah, I guess like I went through electrical engineering in the late 60s. And, you know, in the final years of my program, I got very interested in microelectronics. You know, people were sticking 4 transistors on a chip, and, you know, even some were getting up to 10. That was about the state of development then. But obviously it was a very exciting area, and, you know, going to be plenty of progress in the future. And, you know, I guess the semiconductor course, we had a lecturer that had difficulty explaining the concepts clearly. And they tended to be the courses that I did best in, because, you know, if you could understand what the lecturer was saying, there was no need to worry about it. You knew you'd be able to study up for the exam and get through that subject. But if you didn't understand the material that's getting presented at all, I was forced to put in my own work, you know, try to learn what the lecturer was talking about. So I ended up topping the course in semiconductors, because I had put so much effort into trying to understand the basic concepts. So, you know, that combination of interest in semiconductors and microelectronics. And I won something called the 3rd year traveling scholarship based on my, I think it was my pass in 3rd year electrical engineering, which gave me 80 Australian dollars, which is about 60 US dollars. And the aim of that was to see the world and explore, you know, the topics that you're interested in, you know, visiting industry players in that area and all that kind of thing. So I hopped in my old car and drove down to Sydney and Melbourne. I was studying in Brisbane, and like it's about 1,000 kilometres between Sydney and Brisbane, and another 1,000 to Melbourne. So a fair drive, and particularly in that era when the roads weren't as good as they are now. And then I visited microelectronics places in Sydney and Melbourne, where most of the action was happening in Australia. And, that sort of reinforced my interest even further, getting to meet some of the key players in the Australian industry back then. But I also saw my first solar panel on that trip. That was in 1969. And, the interest in terrestrial use of solar was just sort of starting to develop then. And so that was quite early to see a terrestrial panel.
Yeah. So you saw that on that trip, and it struck you, or how did it exactly happen that you moved from semi to PV?
Yeah, well, I guess I just knew what a solar panel was. The engineer that showed it to me sort of explained how it worked and that kind of thing. So I knew what a solar panel was from that point in time.
Yeah, and that was at UNSW or Melbourne.
That was at a company called AWA Microelectronics. I was actually visiting them because they were building transistors in Australia and starting to build integrated circuits. Largely sponsored by the defence industry. I thought, they had to be manufacturing their own semiconductors to have a viable defence industry. So I was visiting mainly because of the microelectronics, but I was shown their transistor production lines as well. And then I was shown this solar panel, it was just sitting on top of a cupboard actually. So I didn't really get to handle it or anything, but it was pointed at and its function was explained to me.
And they made it themselves, or?
No, it was actually made by, I can't remember who actually made it. It might have been Philips, because Philips was very early into developing terrestrial panels. So they certainly had terrestrial panels in 1969.
Yeah.
So I think it may have been a Philips panel.
Okay. And then when did you start your science career in PV?
Yeah. Australia is a member of the British Commonwealth of Nations, and there's a scholarship scheme that allows students to do postgraduate study in Commonwealth countries. So it's a well-developed scheme, and you get all your airfares paid and all your living allowances and all that kind of thing. So I'd put my name down for a Commonwealth scholarship in the countries where I thought they'd be more advanced in microelectronics in Australia, which was the United Kingdom and Canada. And the Canadian scholarship came through first. So bird in the hand, that's the type of thing. I accepted it and got ready to go to Canada. But there's some, I can't remember exactly why I had to stay in Australia for a while. Maybe it was visas and passports coming through or something like that. So I did a master's, and that was very important in my solar career, I guess, because I wrote one of the early programs, like PC1D or, the more sophisticated programs that are out now that solve the semiconductor equations that determine your carrier transport and so on within solar cells and transistors and so on. So I actually wrote it for transistors. But, it was probably in the first, 4 or 5 programs that were written that did that kind of thing. It wasn't the first. So I did a master's thesis, and what I used that program for was to look at the differences between first order theory and, what the computer was saying. It's just looking for areas where there was a difference between the standard theory and the computer simulations, which was really great because it forced me to understand both the standard theory as well as understanding, how devices deviated from it. So that really gave me a very good understanding of the basic principles of, bipolar semiconductor devices. Yeah. So, mainly transistors I looked at, I guess, but, diodes were something simpler even to look at, and looked at them as well.
Mm. And when did you make your first solar cell, or was it the simulation which you applied to solar cells? When was it really PV in your career?
Well, I made my first cell in 1971 when I went to Canada. So my school in Brisbane didn't have the the necessary gear to make semiconductor devices. So it wasn't really possible to make them there. But when I went to Canada, they had a lab set up, and my supervisor that I chose there, he was working on tunneling MIS structures.
All right.
So, tunneling would be, this was 1971, and the Nobel Prize for Physics was awarded to 3 gentlemen who did different things with tunneling in various semiconductor structures. So tunneling was a pretty hot topic there. And my supervisor was just interested, like the MOS device was starting to become popular in microelectronics, but he was interested in what happened when the insulator layer became sufficiently thin that you got tunneling between the metal and the semiconductor. So just, was there anything interesting that happened when that occurred? So that was the topic that I was given, and I was able to adapt the computer programs I'd written for my master's to incorporate the tunneling structure. So did quite a sophisticated job of that. In fact, like I've seen simulations that have been done recently on the tunneling structures that have taken over the industry, but in some aspects they weren't as sophisticated as what I was doing back in 1971. So that became my topic, and my job was, because I did my PhD in engineering physics, but because I had an engineering background, my topic was, not just to study currents and so on in the device, but look for possible applications for them. Mm-hmm. And so I was looking for ways you could use these tunneling structures, and there was all kinds of transistor structures that looked interesting, and I wrote a few papers on those. But my supervisor had a project with the Atomic Energy Commission of Canada, and that was to make long life cardiac pacemaker batteries. Mm-hmm. What the project he was working on, you use a radioisotope to blast electrons onto a solar cell, and it provides power as long as, well, I guess, like 10 years was the type of time frame that we were looking at for the project. And he had a couple of students making conventional cells for that structure. But what I'd shown was these MIS structures, if you designed it properly, it required extreme metal work functions. You could get structures that were the equivalent of a PN junction diode, except you didn't have any diffusions or anything. So in some aspects, it was cleaner than a PN junction diode. And when we used them as generators under these radioisotopes, we got much higher voltage from them than we did from the conventional PN junctions. And just looking back at some of my results now, it was about 670 millivolts under, 1 sun equivalent was the types of voltages I was getting in that era, when the best conventional cells were probably doing 610 millivolts or something like that. So that's the type of advantage I got over the other structures that people were looking at for these generators. So said, oh, well, I'm onto something here. The only trouble was, that you could blast the electrons through the metal contacts that you're using the top of the cell, but light had more difficulty getting through the metal than electrons. So, when you're using electrons as your source of, photo excitation, the metal in the way wasn't a big problem. Whereas once you tried to use it for light, you had to find a way of getting the light through the metal. So you can make them very thin, which is very difficult, or you could use grating structures. So that got me interested in grating structures for photovoltaics.
All right. And then you returned to Australia and the UNSW, and you formed a team that really shaped much of the industry right through today. And how did that team come together? How did it evolve when you returned to Australia?
Yes, I returned to Australia in 1974, so this is my 50th year at the University of New South Wales. But it was at the beginning of, like the large programs, particularly in the US, for looking at the terrestrial applications of photovoltaics because of the oil embargoes that had happened in the, starting in 1973. But the US, under President Nixon, actually started Project Independence, which was a big program to wean the US from Arabian oil, was the official target. And some of the photovoltaic enthusiasts, which were mainly space cell researchers that were working in the space industry, or space cell engineers, probably there wasn't too many research divisions within those companies, mainly product development, I guess. But they pushed the cause of photovoltaics. But back in that area, nuclear was thought was going to save the world, and one of the nuclear engineers said, that's going to have as much as impact as a flea on an elephant's back. Is what was the comments of the era. But but anyhow, they managed to push it through, and of course the cells were horrendously expensive there, so it was a bit of a push. But they managed to convince people that there was some chance of reducing it down to competitive costs. So that started a big program. In fact, like just in dollars, dollars of the day, there's more money going into photovoltaics research in the US then than there is now. That's without accounting for inflation. So there's something like 200 million, at its peak of that program going in per year. So it was, it was quite a big program, and it covered it was managed by the Jet Propulsion Laboratory, who I understand, did the program, supervised the program that put the man on the moon. I'm not really an expert on that topic, but that's what someone told me. But they used some of the strategies they had done in, developing technology they needed for tasks like that, applied it to photovoltaics. So they'd get people to submit proposals on a topic they were interested in, and they'd pick the three best, and they'd have those three companies competing against each other, and then one by one they'd drop them off. Someone's funding would stop, and then more funding went into the ones that were still left standing. So that was a very large program covering just about every aspect of photovoltaics. And a lot of the technology that's around today, like continuous Shokrovsky and diamond wire sawing and fluidized bed reactors, they were all studied under that program and actually got those technologies started.
Mm-hmm. Sorry, you got funding through that Nixon program, or?
No, but it made it a hot topic in Australia as well.
Okay. So Australia said we should work on this area as well.
Yeah, well, so did Japan. Japan was probably second in, and then Europe, and then Australia, probably in that order. But Japan started a very big project as well, the Sunshine Project, and it was really very exciting times to be involved in photovoltaics because there was so much effort. And in the US, it was all the good labs, that were involved in the program, all the top researchers, in microelectronics that sort of moved into there because there was money available for research in this topic area. So, very exciting times. But NASA Lewis, who was always also doing its own programs, independent of this, had decided that they wanted to improve silicon space cell efficiency, and they had determined that improving the voltage was the way to go about it. Textured cells had just become available in 74 using pyramidal texturing and so on. So the currents had jumped up. So they figured the currents were just about as far as you could take them. And back surface fields had been incorporated in the early 1970s. So they figured, the current, not much more you could do with that. But the voltage, like 610 was regarded as pretty good value. And, you do the calculations and you should be able to get over 700 millivolts. So NASA started a program to try and improve silicon cell open circuit voltage to 700 millivolts. So they had their own researchers working on it and had about 6 or 7 other subcontractors just trying to, like Westinghouse, Motorola, a couple I can remember, and universities working on improving the voltage of silicon cells. And we weren't initially part of the program, but with our tunneling structures, we were able to get well ahead. And of course, the voltage is dead simple to measure. We didn't need to worry about the light getting through the metal even to measure it. You could just collect the current peripherally and work out what your effective open circuit voltage was, or we use very coarse grating structures. We weren't worried about the current density because the voltage only depends logarithmically on that. So, and we had like 50 or 60 millivolts advantage over the rest of the mob because we were using essentially TOPCon back then. And so we streaked ahead of all these NASA subcontractors, and that brought our work to international attention. And like I'd set up this lab, and there was literally no equipment at all to use. But these tunneling structures were really very simple to make. You just take a P-type silicon wafer, heat it in a furnace at 600 degrees to grow the oxide, and you didn't even have to have oxygen in there to do that. It's more the temperature that determines what you get. And then evaporate aluminium onto the front, and that gives you your rectifying contact. And then you mess around with the back of it to get rid of the oxide and evaporate aluminium onto the back, and you've got a solar cell. Or maybe we put the aluminium on the back first, come to think of it, and that during the firing of that, we actually grew the oxide on the front. So it was even simpler. But so the structure was dead simple to make. So, we only needed fairly rudimentary equipment to do that. And then, we just need lamps and stuff to be able to measure the voltage. Yeah. So it's very, very simple. And
so this puts you on the global map for solar cell excellence.
It did. And in 1980 we got an invited paper at the IEEE PVSC conference, and in those days no one used to get invited papers, so we might have been the first ever invited paper at that to talk about our high voltages, because people could see we were onto something that was going to lead to much better cells down the track, I think. But so that helped us get local funding. By then, Australia had cranked up its solar program, like a little bit later than the US and Japan, but it started its program, so there was money available locally. And then in those days, applications for funding were generally sent overseas for assessment, and everyone overseas, had heard of what we're doing and everything, so we got good assessments back. And we were able to buy things like evaporators and furnaces and that kind of thing. And we said, we're going to make a good solar cell. Now we've got these high voltages. We got very close to 700 millivolts. I think 694 was our record. We were desperate to get to 700, but we never quite squeaked over, in that era at least. So we said we're going to turn this, nearly 700 millivolts advantage. The next best was less than 650, and at that point in time, maybe 640 or something. So we had this huge advantage in voltage, and we said we got to be able to make a better cell, but it requires fine line fingers and conductive fingers and anti-reflection coatings and all that. So much more sophisticated processing. So, but by then we built up the funding to allow us to buy that equipment and install it. So we got our first world record in 1983 using these tunneling structures. So the best confirmed efficiency then by present standards was 16.5%, and that was Westinghouse or someone like that. And we got over 18% confirmed. It was actually 18.7, but by 18.1 by present standards. There was a bit of a mess up. NASA was the keeper of standards until SERI got fully established. That's the former NREL, well, now NREL, the predecessor to NREL, and they set up their own cell calibration capabilities and everything, and found that NASA standard was a bit out. So all the efficiencies took a bit of a knock down in about 1983, I guess it was, or maybe even a bit later.
Yeah.
But you know, so the efficiencies from that era, you know, get knocked down. So 18.7 is now regarded as 18.1. So it was the first cell over 18% efficient, when you know, the previous best that anyone had measured in the sort of modern era was 16.5. So it's a jump.
Yeah. So let's we'll come back to technology later on. I was just wondering again, because you mentioned that, you know, nuclear was considered to save the world. You mentioned previously, and but when you look at where solar is today, did you envision back then that it could be so cost efficient and then contribute to such an extent to the global energy supply? Was there a driver back then, or was it just a research project?
Yeah, no, it was a driver. Large scale application was the driver. So the guys involved in setting up the solar program had figured out that 50 cents a watt in whatever the dollars of the era were. Early 1980s dollar was the cost you needed to compete with conventional, you know, large scale generated electricity. So 50 cents a watt was the official target of the large US program.
Okay.
And the aim was to get there by 1985.
Okay.
So that was a specific goal and timescale. So this money was getting pumped in to drive the progress towards that goal.
Yeah. And there was a clear roadmap that showed the path to that, to these 50 cents, or was it, what was the concreteness of that you could take it from where you were to these 50 cents?
Yeah, so there was a number of parallel paths, you know, like continuous Sikorsky was one, and then wire sawing the ingots that are produced, you know, sort of very similar to the type of thing today. You know, ribbon growth was very popular as well.
Okay.
So that was a lot of effort and funding was put in. Mobile Solar and Westinghouse were the big proponents of ribbon growth. So they had two completely different ribbon growth methods that were highly funded. And then a lot of interest in cruder grades of silicon, so metallurgical grade silicon, refining that up to something useful for solar cell fabrication was, you know, another goal of the program. So they had all these parallel strands, and then as they developed, and they had groups just doing the costings of the strands as well. So that there was sort of independent costings of the strands going on as well. And then they'd make decisions about which ones were looking most promising and which ones were going to get to 50 cents by 1985. So, yeah, it was a very well managed program and well funded, as I mentioned before.
Yeah. And 1985, so it was within a few years. Did you actually achieve these 50 cents per watt? Or, I mean,
well,
it's hard to tell because in terms of inflation, it's hard to tell what that actually is. When you look at the learning curve, could you find that spot on the learning curve?
Yeah, so there was an Iranian hostage drama that helped dispose of President Carter, and President Ronald Reagan got in, and he wasn't at least bit interested in renewables. So his big funding program was Star Wars, which was a missile defense system for the US that could intercept anything coming remotely in their direction. So all the top US semiconductor people that were working on photovoltaics got dragged off into Star Wars programs because that's going to get funding to support their graduate students and things. But Australia, being a little bit slower in taking up programs, we're also a little bit slower shutting them down. So we maintained a bit of momentum through the first half of the 80s, whereas a lot of the US groups fell by the wayside. Yeah. So ferry had been established, and it survived right through from the 70s to the 80s. Adolf Gerzberger had set up the Fraunhofer Institute in Germany, and it survived through and we survived through. So we're the three groups that I'm aware of that were sort of making an impact in the photovoltaics area that survived right through from the 70s to the late 80s. To 86, I guess it was, with Chernobyl, which was really kickstarted the solar programs again then, but it was a bit of a barren era. And we managed to get US government funding, even though it had been cut back during that era, because we were setting all these world records for cell performance. We had what were declared to be unique capabilities, which made us eligible for US Department of Energy funding. So it wasn't a lot by US standards, but the Australian funding sources were a lot smaller. So it gave our program a real boost, being able to tap into both US and Australian funding. So that was an important part of our reason why we're able to survive through the 80s. We managed to get support from the US as well.
Yeah. So solar made a fantastic evolution, and you followed it through right from the beginning, or almost from the beginning. I guess Becquerel was a bit earlier than you. Anyhow, is there a, you see the whole evolution? Is there anything that could stop the solar industry by now? Do you think there's anything that?
No, I don't think so. Although when coal fusion started getting talked about in I guess it was the mid 80s. Oh, maybe this is the end of the road. But we had a stranglehold on palladium in Australia, because we were using titanium, palladium, silver contacts for our cells, which was the standard in spacecraft in that era. And we had a lot of palladium in stock as a consequence. And then for these coal fusion reactors, you need palladium. So we were positioning ourselves with the groups that were trying to get into this coal fusion area by feeding the palladium to them, only if we could be partners in what they were doing and all this kind of stuff. So we had our bases covered if the coal fusion had to prove to be real.
And today, do you think anything can come close to solar and wind?
I can't see anything. So fusion of still seems a long way off to me. And then like I went to a conference hosted by the Dutch Academy of Science in 1991, and they were looking at long-term energy supply options. And they had actually not only given up on fission back then, but also fusion, because of the neutrons that are generated. So like people say, fusion's got no radioactive waste and everything, but apparently you have to replace the container walls every 3 years because the neutrons activate the impurities in the steel, and they become radioactive, and you've got to send robots in to dismantle the walls and all this kind of stuff, and then handle the waste responsibly. So they had invited neutronic fusion people along, who were the worst possible ambassadors for the normal fusion people, because their mission in life was explaining how bad conventional fusion was and why you needed a neutronic fusion, which you need some fairly rare materials to get it to work. And it was like a 10 times or 100 times more difficult than conventional fusion to get going. So I said, well, fusion is looking a little bit difficult, because everyone said back then there's no radioactive problem with fusion, but all these fusion experts are saying, oh yeah, there's a hell of a radioactive problem. It's not much better than fission. So that's the story you're getting from these neutronic fusion people. So, even if you get fusion going, it's not clear that the radioactive waste problem is going to be, it's not going to be negligible, I guess, is the best way of putting it.
Yeah. Cool. Yeah. So we've seen this growth, and we are now at least from the production capacity somewhere around 1 terawatt, right? And with shipping around, let's say, 0.5 terawatt. At what level do you think there will be a saturation of the manufacturing base? So Pierre Verlinden and team, they usually bring forward 3 terawatts will be the level of annual shipment where we saturate. I just talked to Jenny Chase, and she said, well, I think she thinks that 1 terawatt shipping per year will be the kind of a saturation level. What's your take on where in terms of volume, annual volume, we will go for?
Yeah, I like Pierre Verlinden's analysis. Get up to the 3 terawatts is enough to replace 90 terawatts or something a year of total installed photovoltaics.
Yeah.
But there's this thought, that photovoltaics is already, according to the International Energy Agency, providing some of the cheapest electricity in history. But the exciting thing is the costs are going down. And, if we can get tandem cells working, the cost is going to go down even further. And still, there's still a lot of development to occur with just standalone silicon cells, I believe. So there's some people talking about this third energy revolution where we have this super abundant energy, 100 times more than we use now, available from solar and wind and so on, that are going to be incredibly cheap. So what does that mean for the future of the human race? So they're starting to ask questions like that. So maybe we will open up a completely different era where we conceive of energy in a completely different way, which might mean that the 3 terawatt level just gets completely swamped.
Yeah. How to predict the future. And when you look at the learning curve, we touched it already a few times. Now we see these record low prices of, let's say, 10 cents per watt. Is there a bottom line? It's so hard to imagine that it keeps going and going, but in a way it does. And the slope is still at the, let's say, since 2006 on the 40% learning curve rate. Overall, it's 25 or something, but just the last 10, 20 years, it's been 40%. Where does it take us, right? Will there be a level where it converges to a stable level? You just mentioned tandems.
Yeah, it's we could see 5 cents a watt pretty soon, actually. Like, according to PV Insights, they're selling modules now for 8 cents a watt, so 5 cents is not all that far off. So it's a little bit hard to say. So I'm on record in 2002 as saying $1 a watt is as cheap as you'd ever get with crystalline silicon. So I'm a bit careful about making projections about lower costs. I did say, however, some time back that would be at 10 cents a watt in 2025. So we're there. So I was correct on that one, despite COVID. So I got a bit worried when COVID started knocking the prices around, but we made 10 cents a watt by 2025 quite comfortably. Yeah. So I'd say we're definitely going to see 5 cents a watt. Are we ever going to see 1 cent a watt? Maybe. Yeah. So this guy Ramez Naam, who's a blogger, he used the terminology solar's going to become insanely cheap. So I'd say 1 cent a watt is probably insanely cheap to my thinking. So we might get there. Because the industry is still in its infancy, and I don't really see silicon lasting forever. Like, if we can develop tandem cells, I think the ultimate technology would be all thin film, which has the potential to go really low cost. So 1 cent a watt might be feasible with a like a 6-cell tandem made of thin films or something like that.
Yeah. We'll touch base on perovskites and tandems a little bit later. I like to sidestep a little, because we're talking about taking decisions, and which, particularly as a professor, a leader of a group, you have to make decisions on which route you take. What were your basics for decision making when you look back at your general technological route you took? Which principles guided you? How did they evolve? And also, maybe the last 10 years, which principle have you added until today for where you want to take your team?
Yeah, I guess we're always guided by theory. So we try to interpret the experimental results we got in terms of what was happening in the cell and what was causing that and causing that. And even if our theory was wrong, it sort of gave you a strategy for changing things and, you know, trying something different. So yeah, so we'd be guided by theory, but if you know, one course of action proved to be a dead end, we'd then look for another course that would prove more productive, I guess. So yeah, it's sort of a difficult area, I guess, the solar cell processing. You know, like we do a lot of work with optics, of course, in making the cells, and that sort of works more or less as it should. If you design something on paper optically, you know, and you make it, it generally worked quite close to what you predicted. But with solar cell processing, there's so many interacting parameters that trial and error was the decider about you know, what processing courses were productive and which were not. So yeah, so we were always guided by theory, I believe, but always had a theoretical model of what was going on, and sometimes we were way off beam in our understanding of what was going on, but it always drove, you know, what we did in the next step. Yeah. And I was fortunate having a strong group, you know, like Stuart Wenham and Jinhua Chow and Awa Wang. They were leading our high efficiency cell program for most of our history. And they, you know, just a group of four of us sitting around, we just brainstorm. And Chow and Awa were very good experimentalists, so we do little sub-experiments around the basic processing just to get a better idea of, you know, what that particular aspect of the cell design was contributing and so on. And you know, we consistently made progress for, you know, I guess close to 30 years.
Yeah. So the, let's say, theory-based approach, that's interesting, right? Because that we can trace back right from to your master thesis, right, where you did the simulation program. So you're really always about the core physics. And I think that's actually, you could think that's natural, but I would assume that not every group leader really goes back to these basic simulations. Interesting aspect, right? So that's like a guiding principle I would see now from the outside. And you just mentioned a number of your coworkers. How did you meet? How did you find? How did that the 3 or 4 of you just mentioned as a team form?
Yeah. Well, Stuart did electrical engineering at the University of New South Wales, and I was one of the lecturers in the courses there. So the solar cell course was a postgraduate course, and it formed the basis of my book I call my Red Book, you know, Solar Cells Operating Principles and so on. So that was basically the lecture notes from that course. But Stuart, as an undergraduate, and he was top in his year, he got the university medal, which means you come top by miles sort of thing. He wanted to do this graduate course, and you need permission from the lecturer to do it. So he came to see me and asked if he could do my graduate course. So, you know, I asked him a bit about his background and everything. So we got to know each other, and then he topped that course as an undergraduate. And you know, got quite interested in solar cells. He was an electronics guy, you know, but before then he was very good at designing electronic circuits and all that kind of stuff. So when he graduated, he got 13 job offers, but Australia had just set up its first solar cell manufacturing line. This was in 1981, or it was in the process of setting it up. And my first PhD student, Bruce Godfrey, had got headhunted to be the managing director of the company setting up that line. And I guess I introduced him to Stuart, or they got to meet somehow or other. And Stuart got 13 job offers, but he accepted this one with the solar cell company because he was interested in that technology, and doing my course had only got him more interested. So he was sort of, you know, wanted to proceed along that direction for his career. So this company was called Tideland Energy, and they had bought the very best technology that was available in that era, which was the screen printing technology that Spectralab had developed in 1974, and then in subsequent years as part of this large US developmental program. But they used texturing of the cell and then screen printing of the silver paste on the top and screen printing of an aluminium paste on the rear. So it was sort of like the modern, the back surface field technology that prevailed until PERC took over in 2018. I think PERC finally pumped it off its perch. But that was basically Spectralab technology that leaked out from Spectralab in several different ways. But Tideland actually bought the technology from Spectralab, so they were honest broker. And Stuart got to interact with these people that had developed the screen printing process, so he's expert in that. He was basically the only technical person in the whole establishment that was setting up this production line in Australia, which I think, I can't remember. Maybe it was 100 kilowatts production capacity, which was massive for that era.
Yeah. You just mentioned PERC. I made my very own first solar cell with Andrew Blakers in 1993, 1994. And we did it on these 2-inch wafers, and I think it took me 3 days to process 4 cells or something, right? And back then, I would have never ever imagined that this type of technology, because it looked so complicated, right, with the lithography, etc., would ever make it into production. And now we are, almost in the post-PERC TOPCon phase. It's pretty amazing how this evolved. What was your thinking when you found the name PERC, right? Would it ever make it into production? Was that the really expectation, or was it more like a design to study the limits of solar cells?
We were told at the time we'd never make it into production because it was too complicated. So don't listen to the advice that you get given. Would be my recommendation. But we actually started more with the TOPCon structure. So the problem with the metal tunneling structures was you heat it up a bit, and the metals were low work function metals that you needed for P-type substrates, and they're very reactive with oxygen. So everyone's saying, "Well, you're wasting your time with that because the metal's just going to eat through the oxide." So we said, "Well, we'll show them they're wrong." So we did some polysilicon tunneling structures in 1981, and so that was the first TOPCon cells to be made, and we published it as well, although subsequently people have missed it. But the processing was horribly complex. The polysilicon, we had to use someone else's gear, and you had to book it up weeks ahead and all that kind of stuff. Whereas we were used to just pumping these devices through continuously. Having high throughput was always a feature of our fabrication. So throughput, we realized, was important. So we made our world record cells using this tunneling structure, and then Stuart and I were annealing them. So Andrew processed them, and Stuart and I were tweaking them in by annealing them in what was really a pizza oven. Just give him a gentle anneal in, just so we could tweak their performance in a bit. And it turned out we could do a little bit more annealing than what we thought. So we figured, well, the metal must be getting through, probably in filaments, through the oxide, the temperatures that we're taking to and the lengths of time and everything. And we're still seeing similar performance. So that led us to PERC, which was basically a small area contact technology. So we got away from the tunneling structures. I'd suggested the tunnel structures on both sides back in 1976 or something or other. As when I thought of it, I thought that's got to be the ultimate solar technology, with a P-type tunnel contact on one side and an N-type on the other side, and a sort of a slippery slide potential gradient that would collect all the carriers. So we actually switched from TOPCon to PERC because it was simpler to process.
Yeah.
Because we were finding with the TOPCon, we needed different tunneling oxide thicknesses from the sort of field oxide. We'd have a thin oxide underlying the anti-reflection coating, but that could be a lot thicker than your tunneling oxide. And to really tweak the surface recombination velocity in, we needed two different oxide thicknesses. Whereas we went to the PERC, we could get by with just one, and the processing became a lot simpler. There wasn't need for the same level of realignment and all that kind of thing. So we switched to PERC in 1983, and we got our second world record at the end of 93 using a PERC type structure, small area contact. So, in those days, we were getting about 650, 660 millivolts voltage. So, the difference between PERC and TOPCon, you couldn't really see when you were limited to that type of voltage. But they were miles higher, those voltages, than what anyone else was giving. That gave us our efficient advantage.
And could you really envision that these technologies would make it into mass production? Was that really in your mind when you went to the lab or analyzed the function? Would you see there would be gigawatts of these production lines with these technologies?
Well, it probably happened a bit more quickly than what I thought. So we had some PERC patents that we let go in about 1995 because there was other stuff we were doing, like the commercial arm of the university was getting a bit sick of all the patent costs they were having to pay on our account, and we were sticking in more patents. And they said, well, do you want us to pay for these new ones as well as your old ones? You're going to have to make a decision. So we decided in 1995 that PERC was too far off for those patents to be viable at the time. By the time it got commercially introduced, so we let the PERC patents go then. I guess we thought we'd find simpler ways of making the structure. So, the first technology we commercialized was actually the buried contact solar cell that BP used in production in Europe. That was their only European production. They used in production from 1992 up to 2006. But that was basically a selective copper metallization selective emitter. So a bit ahead of its time, but with an aluminium back surface field. We were trying for a more like a PERC type structure, but we never quite got it working as well as we could do with photolithography. But using lasers. So, Stuart, when he set up this pilot line, he had a laser for isolating the cells. So he became very familiar with lasers, and we bought an old laser for our lab when Stuart joined, and the electronics wasn't working and everything, but Stuart's converted them to computer operation and all that kind of stuff. And then we started exploring not just using the lasers for edge isolation, and we actually bought it to scribe out the cells, from the 2-inch wafers. Stuart started investigating their use in processing. So initially it was for texturing the devices, multi-crystalline devices and so on. And then we had the idea of actually pushing the metal paste into the groove area, and then finally to actually using the laser to blast through a dielectric and form this groove in the surface that you could then diffuse heavily and then plate the metal to that groove. And that was the buried contact technology that BP commercialized and sold over $1 billion worth of product under license to UNSW. So that was our first technology. So I guess with these others, like we were looking at getting the full PERC sequence established with the buried contact solar cell, which would have given it a big jump in efficiency. And and the PERC was our ultimate cell technology. So that's where we stopped. We got it to 25%, and that's a target I'd set at the end of the program. And then all my Chinese processors started leaving me to set up companies in China. So the processing team was decimated. And we moved our building location. So our lab was dismantled. So all this happened together. So we said, oh, well, we'll give up on this high efficiency route now. More important to get the cost out of the cells. So we'll look at tandems and thin films and that kind of thing. That's our main priority from now on. Yeah, so I guess that probably was our thinking. We'd find a simple way of manufacturing these complex structures, such as the buried contact cell, which is a really great cell, copper metallization. And BP installed Europe's first 1 megawatt system using those cells in 1992 or 1991 and 1992 in Toledo. And they dismantled it 20 years later, and the buried contact cells had actually done better than the screen printed cells in that same field. So, they were really durable. The copper wasn't a problem. There's 20 years experience there. And, in, I guess, one of the warmer European climates.
Yeah.
So, yeah, I guess that probably was our thinking. We'd find a simple way of processing these more sophisticated structures, get rid of the photolithography, which was a feature of our 25% efficient cells.
Yeah. So you already mentioned that. So there were other trends coming up. There was your silicon and glass activities, and then for some time there was the third generation PV as a big trend with lots of different subtopics. There was then the PERC and TOPCon. So things came and go. You said trends yourself, right? And you saw also other things that failed, just like when we had our few encounters with the silicon on glass. I worked on microcrystalline amorphous silicon, you on the CSG solar activities. What's your general learning when you look back at all those technological trends, how to take decisions, right? You said, you just yourself, it's so hard to predict, right? So you actually, decided for the new topics and kind of didn't really envision that PERC would make it. Is there any learning in it, or is it just the learning is it's hard to predict the future? Is it what can you pass on, let's say, to young professors who have to decide on their route they want to give their institute, right?
Yeah, I guess it'd be, the future might evolve completely differently from what the experts say. So like in the 90s, everyone thought the future had to be thin film cells, and there was plenty of people working on amorphous silicon, like you mentioned. That was thought it was likely to be the winner. But I didn't like the technologies the US groups were concentrating on, cadmium telluride and SIGs, mainly because of material abundance issue and toxicity issues and so on. I said, this is silly, not putting your effort into this. How much cadmium telluride cells are you ever going to be able to make? And, like I calculate about 30 gigawatts a year, which First Solar is about halfway there. So they might get to 30 gigawatts. But, like I could see the industry is going to be much bigger than that. So, well, that's just a drop in the bucket compared to what's going to be needed. And then with SIGs, you've got the issue with the indium and selenium and so on. So it's not clean bill of health, and you're using cadmium sulfide as the emitter layer in those structures as well. So I didn't really like them. So I said, we're having all this success with silicon, and with Eli Jablonovich's work on light trapping, all of a sudden the silicon cells became 50 times thicker than what everyone used to think they could become. So, like a micron of silicon was all of a sudden become 50 microns with the 50 times light trapping. So we were using those in our high efficiency cells. We're using light trapping early on. And so we said, oh, well, if we get this light trapping working well, which we did in the CSG, the optics were really good, but the electronic quality of the material we can never get up to adequate to get the 15% efficiency that was our target. Yeah, so we just thought, well, we can make the silicon on glass technology work, different from amorphous silicon, which we thought, it's got the stability issues, so it might never overcome them completely. Although, I was probably pretty confident in the 80s that they would be overcome. Guys like Stan Ovshinsky were saying all you have to do is add this or that to the amorphous silicon, and it'll be, perfectly stable. So with those type of comments going around, you thought, oh, well, someone's going to crack this, and but never seemed to be solved completely. So we just thought we'll have a crack at this silicon on glass technology, and we got it into production. But by then, and we were following First Solar, like they were a couple of years ahead of us. They were starting at like 5% efficiency, and then going up 6, 7, 8, 9. We said, all we've got to do is follow them, and get up to keep in contact with them, and it will be right. But we could never really get above 10% efficiency with that silicon on glass technology. So it was not high enough. And then when my students started setting up manufacturing in China, like Jiangrong Shi in particular, that sort of pulled the rug out from under all these thin film technologies. So I think I got a diagram of, I think from around 2003, of 12 thin film technologies that were sort of in limited production in that era, and all the efficiencies that, the aim of that diagram was to show these CSG ones, even though they were 10% efficient, weren't all that bad, because some people were selling 4% efficient or amorphous modules and this kind of thing. So made our 10% look pretty good. But all of those got blown out of the water, excepting First Solar. So they were the only ones that survived the crystalline silicon onrush once the Chinese got their teeth into it.
Yeah, you just mentioned Dr. Shi and then many other UNSW students who went to China to establish the Chinese PV manufacturing industry, and you also traveled there multiple times. What were your impressions of China back then? And could you have anticipated what it has become today, the powerhouse of solar manufacturing? Was that a foreseeable future for you back then?
Yeah, well, we had this buried contact technology, and we had sort of nearly a pilot line for it built up at our university. We were supplying cars for solar car racing and this kind of stuff, with it. So we're doing like kilowatt quantities, multi-kilowatt quantities. But so we had this business plan. We said we set up buried contact manufacturing in China, and back then, the Chinese product was regarded as pure crap. So, but even though it comes from China, it's going to be the most efficient product in the world. So we'll rebadge it in some way, and the fact that we're making it cheaply in China will be outweighed by the superb performance of these modules. Because we figured we could do better than BP, with the performance of the buried contact in production. So that was the plan. So we grabbed Jiangrong as translator, and I went to China with the guy that was head of the university's commercial division to try and find a Chinese partner to put this plan into effect. And then we just realized how hopeless China was in 1994. It was, all state-run companies, and the companies that were supposedly involved in cell manufacture, couldn't get the materials they needed to do any manufacturing and all this kind of stuff. And, one company who visited, the whole processing team was out cleaning the managing director's car. So you had this big black car. Cars were rare in China, and in that era, and they were all black. So he had this big black car, and the whole team was out there polishing it while we were visiting. Oh no, this is not going to work. And then, we set up this thin film company, CSG Solar, and its pre-runner was Pacific Solar, and Jiangrong was deputy research director of Pacific Solar. And we'd recruited a lot of Chinese researchers quite deliberately, because we didn't want our technology spreading to the US and Europe and Japan. So we had a lot of Chinese speakers already on our staff. So we figured, in that era, any Chinese researcher would be only too pleased to get an offer to come to Australia and work, in Australia for an Australian salary. So we just got our Chinese people to look around for the best people they could find in China. And we recruited them to Pacific Solar, which was the precursor to CSG Solar. And so many of our teams were Chinese based. And the managing director, David Hogg, you might remember him. He was keen on the ISO certification. He said that was a way for a small company to get the benefits of learning from a large company. So he thought, getting ISO certification for our processes would be good. And we had Paul Besor, who I think still has a high up role in the US Department of Energy at the moment. But he was expert in design of experiments. So we had, all these management tools getting developed through our, ISO certification of our different processes and so on, and procedures. And then we had Paul teaching everyone in design of experiments. So the Chinese cohort that we recruited got trained in these modern management practices.
Mm-hmm.
And they sort of formed the basis of the Chinese manufacturing industry when it got established. So you can just look at all the different companies and see where people have ended up. But, Zhengrong, we were aiming to get into production with our silicon on glass, but our board was a little bit more reluctant than we were about a little bit more worried about the challenges in doing that than we were as, the research team was. And Zhengrong got a little bit frustrated with it all. And he said, I want to get out and do something real rather than fiddle around doing all this development with no chance of getting into production. So things had changed in China at the end of the 90s in that state governments were allowed to keep some of the taxes raised from companies working in their area. So that made them more interested in getting companies in their area that were likely to be profitable and pay taxes. And then the legislation regarding private companies was relaxed to some extent. So one of Zhengrong's, social friends, who was I think he'd done economics as his program, he alerted Zhengrong to the fact that the situation has changed, and Zhengrong became fixated on this idea of setting up a manufacturing plant in China. And, we wanted to keep him because we were about to go commercial with our thin film technology. And, he came to me one day to explain that what he wanted to do. And I said, Zhengrong, you know how hopeless that's going to be, because he was with us when we surveyed the Chinese industry. And he said, things have changed a bit since then. And he said, besides my sons, who were both born in Australia, and his oldest was about 10 years old now, he said, if I don't take them back to China now, they won't ever have the choice of whether they want to fit in to Western or Chinese society. They'll be outsiders forever for life. But if I take them back now, they'll be able to make their choice. Mm. So you can't argue against that. You go with my blessing. So he wasn't at all confident that it was going to be a success. And he had to work hard to raise funding. They visited 6 cities in China. And finally, one of the guys that was part of his team had an old schoolmate in the Wuxi government, in China. And he got interested in their proposal and managed to twist the arms of a few local businesses that were making profits. Like, I think there's a couple of the bigger ones who were white goods companies making stoves, refrigerators and washing machines and stuff, to kick in $1 million each. So he had 6 investors, each putting in $1 million. So that was his bank for setting up China's first commercial solar cell production line. Yeah. And he managed to do it. Largely, and a team of people from our group went with him. And one of them was Ted Spidlak, who he was in charge of our equipment acquisition. So we never had a very big budget, like nothing like the Fraunhofer Institute, for example. So all our equipment we used to buy secondhand from the US, from the microelectronics industry. So in the US, you know, in the California in particular, there's these big warehouses full of this junk, basically all this used microelectronics equipment that are looking for a second buyer. And so Ted got very good at picking equipment from what was on offer, and he actually made good friends with some of the people that were. He's a very social guy. Made good friends with some of the guys that were managing these facilities and whatnot, and they were picking out the best stuff for him and all this kind of stuff. And he was actually staying in their homes and things like that when he visited. So he was really good friends with them. And we were bringing it back to Australia, and we had a team that could commission it. We had to change not only the voltages but the frequencies and things like that of the, get the equipment to work. But we had a team that could do all that. So our lab was built up based on the second-hand equipment. So that proved very useful when Zhengrong had this $6 million to set up the first production line, in that Ted Spitalik was part of the founder group. He was one of 6 founders of Suntech. So he used his skills in procuring second-hand equipment and in getting it going. He did all the plumbing and all that required to set up, a semiconductor facility, in Wuxi.
So the very first production line of Suntech was also mostly equipped with second-hand tools. Is that right?
Yeah, it's mostly second-hand.
Oh, wow. Okay.
Yeah. So mainly from the US. I think it was all from the US actually. But Ted's experience of doing that and in installing it and so on from our lab, and in setting up plumbing and all that kind of stuff that you need in a microelectronics facility. It wasn't comparable to your facility in Telheim. It wasn't as elegant as that, I can assure you. But it worked. And in those days, the facilities didn't have to be all that clean because the back surface field technology was quite forgiving.
Yeah.
I guess it was the aluminium, back contact probably getted a lot of the gunge out of the material. And Stuart was an expert in this back surface field processing, because he set up Australia's first line, and he had been taught by the people who originally developed that technology. So he really knew it very well. So he helped Zhengrong get the technology up to scratch. And Stuart had set up this computer program called the Virtual Factory for teaching our students as part of our undergraduate program we started, which just simulated all the processes involved in a BSF processing sequence. And he had quite realistic parameters. So if you turn a knob too far, you're going to get a cell that's not going to work as well, because you've got, you've etched too much or you've done something wrong in the cell processing. But he had all that sort of in the simulation package. So the students used to have assignments where whoever designed the most efficient cell got the highest marks.
Oh, wow. So basically, was that the first digital twin of a solar cell fab? Is that?
Yeah, the Virtual Factory. So PV Lighthouse has a updated version of it on their site. But Stuart's was the first one, and he was able to use that to train the engineers at Suntech, because it overcame the language barrier. Like the engineers probably could speak a bit of English, but not always all that perfectly. But having this computer program, it removed the language barriers, just about entirely. So, that was a big part of it all. So Stuart played a very big role in getting the technology up to scratch. So Solar World actually visited Suntech, and Zhengrong exhibited at one of the European conferences, I guess it was Intersolar or something like that, and bumped into Solar World. Frank Aspect, and ended up visiting Frank in one of his castles, and over a glass of wine, they decided on an OEM contract for Suntech to supply Solar World with Chinese modules.
All right.
which is a little bit weird when you consider the way things developed later.
Ah, right. Yeah.
But he initially, I think he bought at least $200 million of Suntech modules early in Zhengrong's history, which really set Zhengrong up very well, having this, firm customer. Yeah. So that
okay.
Going with that.
Yeah. So let's jump forward in the future into the present. The Australian government has launched the Solar Sunshot Initiative, which is putting billions towards establishing solar and other clean tech manufacturing in Australia. What would you say? How realistic is this vision, considering the dominance of China these days? And how much international collaboration is intended regarding equipment, know-how, and financing? What's your personal look onto this?
Yeah, it's largely a work in progress, but it's not a naive program. Like, people aren't just going to get handed a bundle of money and go away and do your best sort of thing. I think the payments will be based on production, meeting production targets and that kind of stuff. So it's companies that don't do well won't do well out of the funding program. But yeah, there's some opportunities. Like, there's a lot of talk, at the moment. Like, Australia has 20% of its electricity now supplied from solar, and it's growing quickly. So we're sort of pioneering, I guess, the conversion of a modern grid into a renewable energy grid, in that a lot of the issues with having huge amounts of renewable on the grid already being addressed in Australia. So I think we'll be pioneers of that. And there's a lot of talk about Australia using its cheap renewables, because we buy the panels cheaply from China, to become a green energy superpower is the type of words that are used. Like we mine the most iron ore in the world and export it. And similarly with alumina and so on, we're right up there in terms of the raw ores that are exported. But the thinking is, if we've got all this cheap renewable energy and everyone's going to want green steel for their cars and all that kind of stuff, so we can use all this renewable energy and the fact that the ores are just mined next to the energy sources to produce very cheap processed ores, particularly with steel and aluminium. But silicon is another one that gets a mention, because we got heaps of pure silica. In fact, we export a lot of pure sand to China for their processing into solar grade stuff.
The focus will be on polysilicon refinery, or?
Well, that's one possibility. It sort of fits into this green energy superpower model, where we're going to process our iron and aluminum oils, convert them to metals, or pig iron, or take them at least further along the processing route than they go presently. So that's one thought that's driving a lot of the thinking in Australia, a lot of the forward thinking. And it could prove to be feasible, because we certainly have plenty of sunshine, particularly in the areas where the ores are mined. So that's one thought. So we might get into the silicon refining game, and like China has a bit of a problem there with Xinjiang and the slave labor business and all that kind of stuff, and also the fact that most of their silicon has been produced from coal electricity sources. So I think, like, the European Union is probably going to be more and more discerning in terms of the credentials of the material that's imported into Germany and Europe. So you're going to have a clean bill of health with the amount of CO2 emitted in your silicon refinement, and in terms of not using slave labor and everything as well. So China might be at a disadvantage at that end of the spectrum. People I think people are already paying more for polysilicon made outside China. I just saw a chart the other day that had the price of polysilicon from China and the price from somewhere else. I think it might have been Malaysia, and it was like many times higher. So that might continue if people place credentials they want to see on their polysilicon material. So that's a possibility. And then, like I personally think the silicon processing end is changing too quickly to be competitive with the Chinese manufacturers, like just the availability of capital in China. It's nothing like it here in Australia, and then setting up a production line would take you probably 10 times longer here than in China. So I don't think we're well placed to be down that end. Maybe module assembly, that's a little bit more stable. Maybe we could have some manufacturers there. But, like my concern is that our advantage at the moment is we can produce very cheap solar electricity. So, it's negatively priced at some times of the day here in Australia at the moment. So you can't get any cheaper than that. But, we're going to lose that advantage if we start pampering to local manufacturers. So, I can see that as the danger, and everyone is alert to that as the danger as well. But, once a local manufacturer gets a foot in the door, it can sometimes be difficult to remove it. So, so there's a few risks associated with that, in that this green superpower model relies on us continuing to be able to get cheap panels from overseas. At the moment, China, but hopefully India, not too far down the track, and other countries in Southeast Asia are becoming more and more independent of China, and I think they'll continue to do that as the US tariffs force them to become more independent.
Yeah. We touched base on IP previously, and I would like to come back to that topic. So what's your take on intellectual property? There are promising Australian technology companies like SunDrive, which work on copper metallization. And what do you see that this IP is protected in context also with the global role of solar cell manufacturing and the role on a political level?
Yeah, I think the IP area is pretty complex. Like all these Chinese companies have put in thousands of patents on thousands of different things, so they've got a barrage of patents, protecting what they're doing, even though other companies might think they're violating their original patents. Yeah, but my personal view is, a lot of the original patents are probably not valid anyhow, because we were working on TOPCon in 1981 and published the results, and we actually had some patents taken from that era that actually mention it. So it's so this argument over TOPCon and everything, geez, that's really very old technology. I remember Canica had this patent on 3 bus bar cells that they were threatening all the companies with, and so on. And my textbook from 1982 had a 3 bus bar cell on the cover and a photograph of one that Motorola made in 1978 on the cover page, and in front page, I guess, or front piece of the book. So a lot of these patents are a bit like that. They're not familiar with the literature that goes right back, but I've been through it all, so I'm pretty good at digging out old stuff. So I don't know. I think a lot of the patents that you see around these days, you doubt whether they're really all that original if you look at their originality in the context of what's been done before.
The same holds for perovskite solar cells, right? There's lots of activity around that technology route, and you yourself have been looking into materials that can be used as a tandem in combination with silicon or standalone. What's your forecast on the, let's say, tandem on the multi-gigawatt scale?
Yeah, I think us researchers have failed if we fail to develop a viable tandem. So that's my take on it. But my concern at the moment is there's thousands of workers working on perovskite and no one working on anyone else, essentially, on anything else. So I'm just a bit concerned that the stability issues with perovskite might be intrinsic, and no one ever finds a way around them. So I guess we've got the amorphous silicon history as a predecessor there, like after how many years, 40 years. Still, I would expect that you'd still have the initial stability problems with the amorphous silicon. But I think with perovskites, the stability problems are probably more of a worry in that I don't think they stop. I think the degradation just continues. So there's not very much information about the real-world performance of perovskite modules or silicon perovskite tandems. A lot of people say they pass the IEC test, but they're not geared up for testing a combination of light and heat, which is the main intrinsic problem with perovskite. So anyone that touts that as a reason that perovskites are stable, is not being completely honest, I don't think. So I saw one company quoting, it passed all the tests, same tests as silicon, so therefore you might expect it to be as stable as silicon. That's sort of the wording that was used. So we're working on perovskites and hoping we're the ones that find a way of making it stable. And we're doing a lot of testing of perovskites, but we're also working on other semiconductors. So we hold world record for the pure sulfide CZTS, which is a band gap that's sort of in the right range for stacking onto silicon if it's bifacial. And the only problem is our world record is at 12% efficiency, and it needs to be at least 20%. But I'm a bit heartened in that if you look back on the history of SIGs, it took 15 years from SIGs to get from 10% efficiency to 15%. And then the floodgates opened and it shot up over 20 within a few years after that. So with CZTS, you might just need to find that magic step, the same way that SIGs found its magic step. So and then I have a patent that's really been recently been allowed on a whole new range of families of adamantine semiconductors. That just means silicon-like. That haven't been explored yet. So the traditional adamantine families have been pretty thoroughly explored, although, you're never sure whether you've got the full potential from photovoltaic material when you're, around 12% efficiency. Do you just need one step changed and you're suddenly up to 20? But most of the adamantine materials have been looked at, but we have all these new families that have never been looked at before. So we're hoping amongst them there's an abundant non-toxic combination that will prove as easy to get to 20% with as the perovskites did. That's our hope. But I think if we can't find a tandem, the photovoltaic research community has failed, because it's ultimately what we should be shooting for with perovskites. It's going to just open the floodgates to new low cost levels and so on, and smaller areas required and all that good stuff as well.
So when you say we are working on it and I filed a patent, are you still a, let's say, hardcore scientist every day, or what's your normal day look like these days?
Yeah, very much. I stepped down as director of this ACAP at the end of last year. And Renata Egan is now the new director, and she's doing a very good job. So that means I have plenty of free time. So Renata had really taken over most of the administrative load before I stepped down.
Yeah.
But not only, so I'm more or less free from anything but research now. So yeah, I'm enjoying it. So yeah, making a bit of progress in a few different areas.
Yeah. So what? So you're going to the lab 4 times a week or 3 times a week, or what is your?
Not so much. So like since I joined UNSW, I've done very little work in the lab in terms of processing.
Or theoretical research, like theoretical research.
I've done a lot of measurements. So that used to be my job because, like, as a young academic in Australian universities, you get lumbered with this huge teaching load. So you might get an hour or 2 spare, between giving a lecture or and having to do a tute or, having to mark exams or whatever. So that was suited to measuring the cells. So I used to always be in charge of measuring the cells. But in terms of processing, you just, as you know, you just need that uncommitted times 4 days of it to process a cell from go to woe. And it just wasn't possible in combination with a career. So I used to get information from the people working in the labs, and I'd had enough experience in processing to be able to understand what the issues were, I guess. And so that's my main contact now. I just meet with several different groups, every 2 weeks, and they just brief me on what they've been up to, and we work out what they should be doing going forward and all that. And in face-to-face meetings, they're generally able to kick in a few ideas of different ways of looking at things and so on. So still playing a useful role, I think, in terms of research, management, and supervision.
Yeah, excellent. My standard last question is, what does it take solar to take it to the next level? So what do you see there? We talked a lot about technology. It can be from any other area as well. What's your take?
Yeah, I think it's mainly political now. Like the US needs to be more aggressive in its uptake of solar because, and probably find a way of, like the cost of solar panels in the US is just horrific by Australian standards. And then some of my friends, when they put solar onto the roof of their homes in the US, like it's just mind-boggling how much they have to pay, like several US dollars a watt, whereas there's companies in Australia advertising 6 kilowatt systems for 3,600 Australian, which is like 2,000 US or something like that. And the same system in the US would cost you more like 20,000. So it's just mind-boggling how much they have to pay for their photovoltaics there. So they need to get on a bit with installing solar there. They're sort of lagging behind. I think they're below the world average in terms of the amount of solar electricity that their system that is being fed into their system now. I think it's still below 6%, whereas the world average is now above 6%. And both China and India are above 6%. And they much harder for them to get there than the US.
What do you think what's the reason for the extremely high cost on residential systems in the US compared to Australia?
It's supposed to be all the infrastructure costs, like just all the different rules in the different states and all this kind of thing. You have to do your product for each separate state. And, it just seems to be all those soft costs that completely swamp, the system costs. And then, like I imagine 30 cents a watt for a module in the US would be cheap. Whereas in Australia, we can get them for half that, 15 cents a watt is no problem. Even in single container loads, 15 cents a watt is probably expensive now in Australia for a solar panel. So they're paying at least twice, I think, as much as we pay here in Australia. So that's just all that figuring around with tariffs, which essentially is a tax, I guess. So the US people are getting taxed crazily for their solar panels.
Okay. So when you look at I do have another final question. When you look back at your career, what's the thing you're most proud of what happened during the last decades?
Yeah, I guess you know, we think we've had a huge impact on the industry, you know, not only through our technology being adopted. So you know, like PERC, everyone agrees is ours. TOPCon, we were first to suggest and demonstrate. And then if you look at the history of heterojunction, you know, actually, you know, there was talk about amorphous silicon heterojunctions as soon as amorphous silicon was discovered. And Professor Hamakawa in Japan, he really pushed it along in Japan. But the real progress was made was when Mitsubishi stuck an oxide between the microcrystalline silicon in their case and crystalline silicon. That was in 1990. And, you know, that was the first time that someone got a reasonable voltage, I guess, from an amorphous silicon heterojunction. And then soon later, and the thing about that paper was they cited our work with oxide in the standard silicon cells as the motivation for proceeding along that route. And then not long after, Sanyo introduced their intrinsic amorphous silicon layer, which is essentially an insulating layer between the amorphous silicon and silicon. And that's the technology that got popularized. Although I recently had to write a review piece for the Longi 26.8% heterojunction cell, and they're now using a very thin silicon oxide layer along the interfaces, then the intrinsic amorphous silicon, and then the microcrystalline silicon. So it's like a hybrid between Mitsubishi, who really were first to get success with the, you know, the amorphous silicon, crystalline silicon junctions, and the Sanyo approach. So yeah, so we feel we even have a bit of a claim on the heterojunction work because you know, we motivated Mitsubishi to try it out and it worked. So I guess the technology, we had a big impact, and then you know, the shift of the manufacturing to China is why we have cheap solar cells now, and you know, my guys were responsible for that. So I think I had 6 PhD students that were Chinese, born in China, you know, before 2000, and all of them became founders or, you know, CEOs or CTOs or key personnel for, you know, the first companies that were into manufacturing in China. So, you know, we figure the first 5 companies in the manufacturing in China, 3 of them are actually set up from people by our team. That Ted Spitalak guy just went around China setting up production lines. So he set up 3 in the first 4, I think, that got into manufacturing in China. And then all the Chinese companies, when they were floating on the US exchanges, recruited our people as CTOs and so on, because that's what the US investment banks were expecting as part of their due diligence. And then we have all the students that we've trained, that Chinese nationals who are working in the industry in China. So we've had a very big impact on the reduction of costs through that activity as well. So, you know, not only in the technology, but in the, you know, the development of the manufacturing industry, I think we've had a huge impact. So obviously we're very proud of both those contributions.
Yeah, excellent. Martin, thank you so much for coming onto the show. Thanks for sharing your solar journey. It's been a real honor, and thanks a lot for what you've done for the industry and also the young scientists, including me, indirectly through your book, and yeah, and all the other solar engineers around the world. Thanks a lot, Martin.
Well, nice talking to you, Torsten. Goodbye for now.
Yeah, goodbye.